and welcome to our introduction to sequential circuits. Let's take a look at what a sequential circuit is and the things we need to describe it in its entirety. Sequential circuits are logic circuits which depend on a previous input or a previous output, as well as the current inputs, in order to determine a new, or what we call the next output or state. Sequential circuits are one of two types. They can either be controlled by a clock, which allows the outputs to change only at a certain time, and these circuits are called synchronous sequential circuits and are the most common type of sequential circuit by far. This timing diagram at the bottom of this slide shows a sequential circuit. And what we see here is that the outputs, out 1 and out 2, only change when the clock is going from low to high. That doesn't mean they change every time the clock goes from low to high. It just means that when it's time for them to change and perform the function of the circuit, that they will only do so when the clock is going from low to high. This implies that the circuit is a leading edge or positive edge triggered device or sequential circuit. We say it's leading edge triggered because the output can change only on the leading edge of the clock when the clock is going from low to high. Now another common type of sequential circuit is when the output changes on the downside of the clock, or when the clock is going from high to low, as is shown here for the output Q. So here, Q is changing only on the trailing edge, or the negative edge of the clock. And the terminology we use to describe that behavior is that this sequential circuit is trailing edge or negative edge triggered. So trailing edge triggered or negative edge triggered implies that the output can only change when the clock or the control signal is going from high to low. Now, something else we use to describe sequential circuits are states, and those are shown here on our previous slide. And these states are simply dummy variables that keep track of what's gone before in order so that the next place we go or the next outputs we determine are based on that state. And that allows us to track the history of the circuit and to keep it in mind or in function when we determine the next outputs for the circuit. Now, another type of sequential circuit that's far less common than the synchronous sequential circuit is the asynchronous sequential circuit. It still has feedback and it's still dependent on previous inputs or previous outputs. In other words, the history or the memory embedded in the circuit. But instead of changing only on certain condition of the clock, asynchronous circuits have no clock, and the output, in this case Z, can change at any time. And the difference between an asynchronous sequential circuit and a combinational circuit is that the output Z in an asynchronous sequential circuit changes in response to both the current inputs and the present outputs, which reflect the previous inputs. In other words, the history or the memory of the circuit. So moving on, we can take a look at what this looks like. A sequential circuit can be described by a truth table just like any other logic circuit. And it can also be described in a state diagram. And the state diagram allows us to track all possible combinations of previous outputs, present inputs, and next outputs so that we can track the history and the response of the circuit to that history in its entirety. In the example to the right, we have three different states that we've called S1, S2, and S0. And we can define those in a truth table simply by assigning them some binary representation. In this case, 3 states would take 2 bits to indicate those 3 states. And the states describe both the history and the future of the sequential circuit. So as an example, if we look at S1, when we get an input of 1 to S1, the circuit remains in its present state, S1, and it returns an output of 1. That's just a description, a functional description of how this circuit works. In another example, if we're in the state S1 and we have an input of 0, the circuit will return an output of 1, and it will move all the way to S2. And so on and so forth to the state diagram that describes not only the inputs and what the next state will be, but also what the output is for the present inputs, given both present inputs and the current state. Now we can also express a sequential circuit in terms of a truth table, just like we did with combinational circuits. And to do that, we're just going to translate the state diagram now to a truth table. So now here we've encoded our present state, S1, S2, and S0. We've arbitrarily or randomly assigned S0 a value of 0, 0, S1 a value of 0, 1, and S2 a value of 1, 1. These are random assignments, and we can adjust those if we find a more efficient way to implement the circuit with a different set of state assignments. So now we can look at the state diagram to see what happens given a certain input and a certain state. Starting with a state at S1 and an input of 0, that means we're here, and we're going to go to S2 and return an output of 1. So the next state is going to be S2, which we've encoded as 1, 1, and the output is 1. In the next example, we're still in S1, a state of 0, 1. We have an input of 1, and we can see that with an input of 1 in state S1, we just stay put. So our next state is still S1, which we've encoded as 0, 1, and our output in that state is also 1. Now moving on to S2, in the 1, 1 state, if we have an input of 0, we see the output is 0, and we remain in the state S2. And finally, as an example, if we're in the state S0 and we have an input of 1, then we end up in S1, which is encoded as 0, 1, with an output of 0. So these are not all the possible combinations for this particular state diagram, but these are just a few examples of how we take a state diagram, which describes a problem we're trying to solve, and implement it in a truth table. And once it's in a truth table, it becomes straightforward to implement it using digital logic circuits. So we can ensure that synchronous sequential circuits change their outputs only under certain conditions of the clock by using the appropriate logic circuits to implement them. There are basically two types of sequential circuits in the synchronous realm. Latches, which change their output only when the clock is high or only when the clock is low, and a flip-flop that changes output states only when the clock goes from low to high, called leading or positive edge triggered, or when the clock goes from high to low, called trailing edge or negative edge triggered. Typically, flip-flops are made from several different latches to get the edge triggered rather than the state triggered functionality. The major types of latches are the D latch, which is simply used for storage or to hold certain values until we're ready to use them. The set reset latch, which is what it sounds like, it's used to set and reset circuits when we need to do that. And then the three major types of flip-flops. The D flip-flop, again, like the D latch, is used for storage, and it's made up of two D latches, which we'll see in a future session. The JK flip-flop is relatively complicated and allows us to implement multiple functions instead of just storage. And the T flip-flop, or the toggle flip-flop, which allows us not only to hold a present state, but also to toggle the outputs at will, given a certain condition of the clock. So T here stands for toggle. And we'll review all of these latches and flip-flops in future sessions, as well as some of their implementations. So we've seen here today that sequential circuits come in two different flavors, synchronous and asynchronous. And since synchronous circuits are so popular, we'll exclusively be focusing on synchronous circuits in future sessions. But overall, these sequential circuits are valuable tools to implement digital logic problems that are dependent on the history of a particular problem or circuit. We can store information and take into consideration that memory alongside the present state of the inputs to make decisions in ways that we simply can't do with combinational logic. Well, that's all for our introduction to sequential circuits today. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.